Have you ever looked at a breathtaking digital art piece and deeply wondered how they created that? There are many different approaches to digital art, but shaders might be one of the most powerful and versatile when it comes to creative coding. Shaders are like the paintbrushes of the digital age. They allow you to turn a blank screen into a stunning animation in real time, and they're responsible for the stunning visuals in some of your favorite video games and movies. They can be used by creative developers in order to make 2D and 3D renderings exclusively using code, their imagination being the only limit. Shader art coding is all about using mathematical functions and algorithms to manipulate pixels and create incredible visual effects. It's a unique fusion of art and science, where creativity and precision collide to produce something truly mesmerizing. But what are shaders, you may ask? In essence, shaders are small programs that run on your graphics card and are responsible for calculating the color of each pixel on a canvas. Shaders work by taking inputs, such as the position of the current pixel, and using them to calculate a single final color using the OpenGL shading language, or GLSL in short. It can be seen as a mathematical function that maps a 2D coordinate, the pixel's position represented as X and Y, to an output color which in computer graphics is represented by a red, green, and blue channel. This function is computed in parallel for every pixel on the screen, which means that shaders can perform millions of calculations per second to produce stunning real-time graphics. Since discovering shaders about a year ago, I've also made some of my own. It's really fun to learn a new computer graphics technique and make a shader about it. There are so many topics to learn from and so much space for discovery and original creation that it's impossible to get bored. While they're great at rendering stunning 3D scenes and even 4D for the particularly brave developers, shaders also excel at rendering 2D images and animations. They usually run blazing fast compared to some heavy 3D shaders that require more performant GPUs and compute power. For over a year now, I've been sharing my own trippy animations online, mostly in 2D, in order for shader coding to get known by a larger audience. Doing so, I've received many requests for tutorials and explanations about how to create such visuals using code. In this video, I will walk you through the creation of this shader animation from scratch to give you some insights about how to start making digital art using shaders. Additionally, I will provide some useful references and tools that can assist you on your artistic journey and that will be listed in the description. I assume a basic knowledge of programming, but don't worry if you don't know anything about code. I'll explain every step of the process, including the mathematical aspects, using visuals that, by the way, are also made with code. If you want to follow along with this video, you can head over to Shadertoy.com. It's a platform where you can easily start writing your own shaders and share them with others, and it's a mine of inspiration and knowledge about computer graphics and digital art. I will start from the most basic shader that gets automatically generated when you click on New. Actually, I'll remove all of this to explain from the very beginning what is going on. Each shader is defined inside the main image function and has only two parameters. fragCoord is the input parameter. It is of type vec2, meaning that it's a vector containing two values, the x and the y coordinate of the current pixel. fragColor is the output parameter, and it is of type vec4 because it holds the red, green, and blue channels, as well as an additional alpha channel which stands for the transparency of the pixel. Let's assign a value to that output parameter. Here we set fragColor to a vector of 4 components using the vec4 keyword, then specifying each component's value. The fourth value is the alpha channel. It has no effect in Shadertoy, so I'll keep it to 1. In GLSL, the output color is normalized, meaning that each channel ranges from 0 to 1. By setting all channels to 0, the output is full black. Remember that this code is ran for every pixel to determine its color. Here, the output color is a constant, so it will display a uniform black color across the screen. Similarly, by setting all 3 channels to 1, we can display full white. By playing with all the possible values for all 3 channels, we can produce millions of unique colors. I should also mention that there is a nice Chrome extension for Shadertoy that provides some useful features like this color picker that allow you to convert colors to vectors easily. It's called the Shadertoy unofficial plugin. Now, let's use the value of the input parameter in order to start seeing some better things than a uniform color. The range of fragCoord is dependent on the size of the canvas. For instance, if you're rendering on a 1600 by 900 canvas, X will range between 0 and 1600, and Y will range between 0 and 900. However, when working with shaders, we'll usually want to have these coordinates in clip space, ranging from -1 to 1, so that they do not depend on the current resolution of the canvas. So I will create a new vector called UV, which will contain our transformed pixel coordinates. The first step is to normalize fragCoord so that its components range from 0 to 1. For that, we simply need to divide it by a vector containing the current canvas resolution. Fortunately, there's a global constant provided by Shadertoy called iResolution. It's a vector of 3 components holding the current canvas size in pixels. The first 2 components are the width and height of the output texture, and the third component is the depth and is only used when rendering to 3D textures. As we're rendering on a 2D canvas, we won't use the depth here, and the .xy syntax is used to isolate the width and height components of the resolution so that the division happens between vectors of the same size. I'd like to pause for a second here to discuss an important concept widely used in GLSL called swizzling. Writing iResolution.xy is equivalent to creating a new vec2 and assigning to it the x and y components of iResolution respectively. This concept can be extended further. For instance, if we wanted to create a new vector containing only the y and z components, but in reverse order, we could simply write iResolution.zy. These swizzling syntaxes are valid in GLSL and allow you to easily create, arrange, and reorder vectors into new ones. It's also important to note that when performing operations between vectors that have the same number of components, it acts as a shortcut, applying the same operation to every corresponding component of the vectors. So let's check if it worked. I will display the x value of this new vector in the red channel only, keeping green and blue to 0. We can observe a red gradient that aligns with the fact that the uv.x value linearly ranges from 0 to 1 as we move from the left to the right side of the canvas. In a similar way, if we display the y coordinate this time in the green channel only, we'll see a green gradient going from the bottom to the top. Now, let's display both components at the same time in the red and green channels respectively. The bottom left corner is black because both components are 0, and in the top right corner both red and green channels are at 1, which produces yellow. All other pixel colors contain nuances of red and green that visually represent the value of the UV coordinates. Note that in GLSL, we can simplify the following expression by merging the first 2 channels into one and directly writing UV as it contains 2 values. Now, let's start to transform the space in a way that is more convenient to work with. Right now, our UV coordinates range between 0 and 1, meaning that the center pixel coordinate is 0.5, but it would be preferable to have it exactly at 0, 0, so the center of the canvas matches with the center of our coordinate space. In order to fix that, we can first subtract 0.5 to each component of our UV vector. This will shift the space to the upper right and effectively center it. However, the corners of the canvas now range from -0.5 to 0.5 instead of ranging from -1 to 1 like we wanted at the start. To achieve this, we can multiply the coordinates by 2, resulting in the center remaining at 0, 0, while doubling the UV values of all other pixels to ensure they fit within clip space. As a final step, we can clean up the code by condensing it into a single line and eliminating the parentheses. Now that we have this foundation, our objective will be to write instructions based on the current pixel coordinate to display interesting renderings. There are a multitude of GLSL functions at our disposal, and in this tutorial, we will explore a selection of them. We will start by exploring the length function. This function takes a vector as its input and calculates the magnitude of that vector. Essentially, it calculates the distance between the vector and the origin. Since we have centered our origin, we can utilize the length function to calculate the distance between any given pixel and the center of the screen by passing in our UV vector. This can prove to be extremely useful when creating complex and dynamic renderings. I will create a float value, which unlike vectors contains one single decimal number, and assign the length of our UV coordinates to it. By setting the red channel of the output color to this value, we can observe a radial gradient expanding from the center. It represents the distance between each pixel and the origin of the canvas, transitioning from black to red. Alternatively, we can assign this value to all 3 color channels, creating a grayscale gradient. But before continuing, we need to address an issue with the current code. Everything works fine because our canvas is a square and has an aspect ratio of 1, meaning the width and height are equal. However, if we were to change the aspect ratio by making the canvas wider, for example, we would notice that the circle gets stretched horizontally. This occurs because our UV values always range from 0 to 1, regardless of the canvas's width and height. To fix this issue, we need to multiply the x component of our UVs by the current aspect ratio of the canvas, which is its width divided by its height. This adjustment ensures that we avoid any unwanted stretching or distortion effects, even when dealing with different canvas sizes and aspect ratios. To really be efficient, we can combine our previous UV transformations with this new fix and rewrite it on a single line using basic math simplifications. Now, I will subtract 0.5 from this distance. The expression length UV minus 0.5 actually represents the sine distance function of a circle with a radius of 0.5. A sine distance function, or SDF, is a term used to describe a function that takes a position in space as input and returns the distance from that position to a given shape. It is called signed because the distance is positive outside the shape, negative inside the shape, and exactly 0 at the boundary of the shape. You can find distance functions for a lot of shapes or even make your own. I have linked in the description this article that provides a collection of useful 2D SDFs for various shapes, and this website in general is also a mine of useful tutorials about shader coding. So the gradient we're observing represents the signed distance to a circle with a radius of 0.5. The values are positive outside the circle's edge, which creates a gradient, but they are negative inside the circle, resulting in black. To verify this, let's take the absolute value of this distance using the abs function. This will convert the negative values to positive, and now we can observe that the distance increases as we move further away from the circle's edge in both directions. To achieve a sharper transition, we can utilize the step function. It accepts two input parameters, a threshold and a value, and its output can only have two states. It will always return 0 when the value is less than the threshold, and 1 otherwise. By applying the step function to the D value with a threshold of 0.1, all pixels with a D value less than 0.1 will be assigned the color black, while all other pixels will be assigned the color white, creating a distinct ring shape. However, if we want a smoother transition between black and white, we can utilize the wonderful and magical smoothstep function. It is similar to the step function, but this time takes two threshold values. It assigns the color black when the parameter is below the first threshold, and white when it exceeds the second threshold. Within the threshold range, it smoothly interpolates the values between 0 and 1. This gives us complete control over the range and sharpness of the transition. By using this function, we can achieve a seamless gradient from black to white between the values of 0 and 0.1. Now, instead of subtracting 0.5 from the original distance, I will apply the sine function to it in order to create a radial repetition of the rings. Currently, it only displays a single dot because the sign of a value between 0 and 1 is very close to the original value, resulting in minimal change. However, when we increase the frequency of the input value, we can better see the oscillating pattern of the sine function, which ranges from -1 to 1, and it allows us to generate repeating rings around the center of the image. Note that multiplying the distance by 8 before applying the sine function stretches the space and alters the color intensity, requiring a corresponding division of the output by the same factor. One interesting characteristic of the sine function is its repetitive nature. By introducing a time component and offsetting the distance before applying the sine function, we can create an infinite loop of rings that continuously shrink towards the center. In this case, I am utilizing a global constant called iTime, which is an ever-increasing float representing the number of seconds that have passed since the beginning of the animation. Now that we have a moving pattern, let's focus on improving the visual aspect and colors. I really like to use neon colors, and the inverse function, 1/x, is perfect for achieving that aesthetic. Instead of calculating the final color using the smooth step function on the D value, I will take the inverse of D. As a result, the screen will become entirely white. So let's take a closer look at the graph of the function to understand what's happening. The graph shows a curve with extremely high outputs for low input values that gradually diminishes as the values increase. Since we are working in clip space, any output value greater than 1 will be displayed as white, and the curve tells us that this is happening if we're taking the inverse of any number that is less than 1. However, after passing through the sine and absolute functions, D now ranges strictly from 0 to 1. Consequently, the output can only ever be white. To address this issue, we can scale down the inverse function to ensure that the falloff is visible within our desired range of 0 to 1. It's still a bit much, so let's scale it down even further, and now we can see a pleasant glow emanating from the rings. Now, let's introduce some color into the composition. I will create a new vec3 variable that will initially contain red. By multiplying this color variable with the value of D and making it the new shader output, the black areas will remain black, while the white areas will be tinted with the corresponding color value. Also, here our calculations are not limited to the 0-1 range. We can intensify the colors by setting certain components to higher values. In this case, the blue channel has the highest value, which produces a vibrant blue tint in the final result. To add even more variety to the colors, I will use a very nice function that you can also find on the previous website, and that allows you to create infinitely various color gradients using the power of trigonometry. It produces a color output based on 4 control parameters of type vec3, which are passed as inputs. These parameters dictate the composition of the gradient, enabling you to customize the colors to suit your preferences. While the function may appear complex with its total of 12 parameters, another website exists that has a user-friendly interface, allowing you to visually create your own palettes and gain a better understanding of how the function operates. After playing for a bit, I found a specific palette that I like, and I can use the values provided at the bottom of the page to update my code. These values correspond to the A, B, C, and D parameters in our palette function. Instead of passing these parameters as inputs to the function, I will declare them directly inside the function by creating 4 new vectors that correspond to the palette I created. With this modification, I can replace our constant color with the palette function. It takes our original distance to the center of the screen as input before any transformations. This simple adjustment already adds a captivating and dynamic range of colors to our composition. To enhance readability, I will hide the palette function. Afterward, I will proceed to adjust the input to the palette by adding a time offset to it. This modification will bring additional dynamism to the colors, as the gradient will continuously shift and evolve. Now, let's introduce spatial repetition using the fract function, which is perfect for this purpose. The fract function simply returns the fractional part of its input, extracting only the digits after the decimal point. As a result, its output ranges from 0 to 1. But even if the space has been repeated, it seems that something is not working as expected. To understand the issue, let's display back only the value of our UV variable. We successfully achieved repetition by creating 4 smaller versions of our original UV coordinates. However, each repetition is now confined within the 0-1 range instead of the desired clip space. To resolve this, we can apply the same solution as before, scaling the UVs first and then subtracting 0.5 to center them. We finally have nicely repeated the space, and we can also shorten all these operations into a single line for brevity. Now, D represents the local distance relative to the center of each repetition, but I'd like to keep track of the original distance to the center of the canvas. I will create a new vec2 called UV0 and assign it the value of our UV coordinates before space repetition has been applied. This will allow us to replace D inside the palette by the length of our original UV coordinates, which will break the local gradient repetition. It's now time to add the final touch that will give our composition its fractal appearance, iterations. Before we proceed, let's slightly rewrite the code for what will follow up. I will create a new vec3 variable called final color and initialize it with black. Instead of updating the call value directly, I will add the result of this operation to our new color variable. Finally, we will output this final color as the result of our shader. This modification doesn't change the visuals, but it sets the stage for adding iterations to our code. To achieve this, we will utilize a for loop, which is a common algorithmic structure found in many programming languages that allows us to repeat instructions. We will encapsulate our entire color calculation code within this loop. At this stage, this simple loop won't produce any visible changes in the visuals, as it will exit after just one iteration. By increasing the number of iterations, we can observe the emergence of additional layers and intricate details in our fractal pattern. However, as the complexity intensifies, it may become visually overwhelming. To mitigate this, I will reduce the frequency of the time offset. Iterating this code generates interesting patterns because each iteration involves scaling and repeating the space using the fract function and adds the resulting colors together. However, the perfect matching of repetitions caused by multiplying by exactly 2 makes these repetitions match up a bit too well. To introduce more visual interest, I will break this symmetry by multiplying with a decimal number instead. Now, I will make use of the exponential function to increase the variations further. I will multiply d, which is the local distance to the center of each repetition, by an exponential function depending on the global distance to the center of the canvas. To try and understand how this works, I will make use of yet another website called GraphToy that was specifically designed to graph GLSL functions. I will display the identity function as a reference along with the exponential function. Actually, we're interested in the exponential of -x. We can see that it displays a similar behavior to 1 over x that we used earlier, but this time doesn't go to infinity at 0. By multiplying the original x value with this function, we introduce a smooth and distinctive behavior to our final curve, which blends well with the other effects in our current animation. Considering the current brightness intensity, I will further reduce the fall-off of the inverse function to achieve a more balanced effect. Additionally, let's explore the idea of incorporating I into the loop's calculations. This will introduce additional variation to each layer. To achieve this, I will include I as part of the input to our color palette function, resulting in slight color offsets after each iteration. With the improved visual quality, I believe it is appropriate to introduce an additional iteration to enhance the creation of smaller details. As a final touch, let's utilize the power function to enhance the overall contrast of the image. When the input ranges from 0 to 1, the POW function effectively accentuates the darker colors closer to 0, while having a lesser effect on the lighter shades. Although taking the power of 2 may seem excessive, smaller values such as 1.2 can significantly improve the contrast and visual impact of the composition. We could go on and on, introducing new functions and new variations to our animation as the GLSL language offers limitless possibilities. But I'm happy with these results, and sometimes it is also important to recognize when to pause, take a moment to appreciate what we have created, reflect on what we have learned, and approach new ideas with a fresh and blank canvas.